Okay, so how is everyone today? Good, I hope? All right. So last time, besides the quiz, last time we were talking about monic quadratics, factoring monic quadratics. So that's two different vocabulary words there. So can someone remind us what a quadratic is? Quadratic. Very good. Polynomial of degree 2. And then what does monic mean? It doesn't mean degree 1. Yeah, that one. Leading coefficient is 1, right? So to say monic quadratic means that we're talking about a polynomial which has degree 2 and leading coefficient 1. So it's really kind of like a fairly specific case. So here's an example. One of those, so we can say something like factor z squared minus 17z minus 20. 20? No, 60. What am I saying? Okay. So later in the semester, I wouldn't give you a question this straightforward. So what I intend to say is that when you've seen enough of these, you'll be able to look at this one and say, and sort of like think about it for 5 seconds and say, yeah, I can see it. But but for now, we're on the assigned homework. You've got to do it in this tedious way, of making the table and clearly showing that you're looking through different possibilities. All right. So the way it works is that you want to make a search, and you're looking for two numbers. I'll call them P and Q, and you want the sum P plus Q to be negative 17. That middle number there, and you want the product to be negative 60. All right. And so we want to find two numbers that satisfy two conditions. Now it's easy to find two numbers that satisfy just one or just the other, but the real trick is finding two numbers that satisfy both at the same time. So here's an example. I could say, well, how about say negative 2 and negative 15. Now I claim that those numbers are reasonable, and at least in one way. So why is these two numbers reasonable? Right. So we get negative 17 when you add them, but when you multiply them, you get 30. So can you see that that was good, but that one's not good? All right. Now I claim that you can guess sort of even more intelligently than this, and that is by looking at the product. So now we're looking for two numbers, and the product is negative. So that means that one of them has to be negative, one negative and one positive. Because if they were both positive, the product would be positive. And if they were both negative, the product would be positive. So what I'm saying is that from that view, it kind of really doesn't make a whole bunch of sense to ask about two negative numbers. Right? Okay. So how about, so we're going to need, at least one of them to be positive. So how about, I don't know, 2 and negative 19. So one negative and one positive, that's good. And then if you add them together, you get negative 17, that's good. But then if you multiply them together, you get negative 38. That's not good. But at least the product has the correct sign now. We're looking for a negative number, and that's a negative number, so that's a little better. Now, if you've like maybe currently run out of patience for making this one work, maybe you try this one. So now I'll try two numbers that make that one work. How about 2 and negative 30? So that's a reasonable pair to inspect, in the sense that when you multiply them together, you get negative 60. But when you add them together, what do you get? Negative 28, right? So can you see, like, it's always possible to find two numbers that satisfy either that one or that one. The trick is finding two numbers that satisfy both. All right. So now I've, messed around enough. Can anyone think of two numbers that'll do it? Negative 20 and 3. Okay, negative 20 and 3. I see that just off the top of my head that one's negative and one's positive. That's good. And then when I add them together, I get negative 17. That's good. And when I multiply them together, I get negative 60. That's good. So can everybody see the name of the game? So what I'm saying is right here at the beginning of the semester, when we're first learning this technique, I need you to write out this table so that I can see that the process is working inside of your head. I'm not a mind reader. But when we get past this place, you'll still be factoring quadratics, but that'll just be one part of some bigger thing that you're doing. And I don't need you to show that much work in those places, because it's in some sense the other bigger thing that I'm interested in. Okay, so as a result, we found two numbers, and we can say, therefore, the answer to the question is z minus 20 multiplied by z plus 3. And then, if you're not confident that this is the answer, you can always check this. How do you check it?
Multiply them all out.
By multiplying it out.
Expand.
Right. So you just check it like that. Now, here's another view. Another view. So, specifically, this thing that we're doing here, that we did here, it only works for monic quadratics. So, like, if I gave you an exercise where the quadratic wasn't monic, then this wouldn't work. So, I'm going to look at we're going to see another way to look at this that's going to be seemingly pretty long-winded. But the reason that we're going to look at this easy problem in this relatively complicated way is because this is going to be the only way to look at it for the non-monic case. All right. So what we're going to do is we're going to take z squared minus 17z minus 60, and what we're going to do is we're going to use those two numbers to split negative 17z. So you'll see what I mean. So I'm going to say that this is equal to z squared. So that one is that one, and then subtract 60. So those are the same. And then what I'm going to do is I'm going to take the negative 17z and I'm going to split it like this. I'm going to say, all right, this will be subtract 20z and then add 3 more. Okay. So I'm not claiming that it's clear why I'm doing this yet, but at least I haven't made an error yet. Okay, now because notice that this first expression that we were given had 3 terms, but now we have another one that has 4 terms. Now, because we have 4 terms, I'm going to make, now it's possible for me to make 2 groups of size 2, because addition is associative. And I'll say this. So this is z squared minus 20z, and then plus 3z minus 60. All right. So now in each group, I'll make the following observation. For example, in the first group, this one right here, what's its greatest common factor? Z. So I'm going to factor out the GCF for that one. So this would be z multiplied by something or other. Okay, and then for this group, what's its GCF? 3, right? So I'm going to factor out 3. And, to complete that process, we need to fill in those parentheses. But, in case you look at the notes later, I'm going to leave that line there, just so you can see it. See that there was a question to ask. So for this one, what do I need to write in there? Z minus 20. Gesundheit. Gesundheit. Okay. Then how about for this group? What do I need to write in there? Z minus 20? I thought I wrote Z minus 20 in there. Nah, it's the same, isn't it? Now you might ask, is that a coincidence? And the answer is, no, that's not a coincidence. It had to be that way. It had to be that way. Now, Z minus 20 has occurred in both places. So now, if this were an x, if I was covering up an x, then this would be zx, and this would be 3x, right? So zx, 3x. Well, then we'd be able to factor out the x, right? Because that thing would be common. If it was a w, zw plus 3w, we could factor out a w. So now, it looks weird. It's a z minus 20, but all that matters is that it's the same thing in both places. That means that we can factor it out. And so if we factor out that z minus 20, then what do I have to write in those parentheses?
Z plus 3.
Z plus 3. So is that the same thing that we got in the other way? Yeah. So the factors are in a different order, but that doesn't matter because multiplication commutes. Okay? So that's interesting. Now, so to reiterate, for this exercise, this work is what I expect you to produce. Not this stuff. So you in my view would reasonably say, okay, fine, but then why do we do any of this at all? Okay, that's because we need to be able to factor the non-Monic case, the case when the leading coefficient is not 1. Okay. So here's how that works. So here I'm going to make a little hidden block. So you can kind of imagine that this is me back in my office making you an exercise. So the way these actually work is that I do them backwards. Is that I choose the final answer. I choose the factorization, and then I make a problem that will have that factorization. So I'm gonna choose the factorization here and now. I'm gonna say, okay, I want the final bit of the answer to say 4w plus 3 multiplied by 2w plus 5. So that's going to be, the final bit. So now I'm going to multiply it out and collect like terms. So that'd be 8w squared plus 20w plus 6w plus 15. Okay, and under normal circumstances, you wouldn't see this part up here. So here's the question. So please factor 8w squared plus 26w plus 15. And of course, the final answer is going to be that. But, that's not going to be given to you. And besides that, what's being graded is the actual work. So now, this is a quadratic because it's a polynomial of degree 2. Is it monic? It isn't, right? Its leading coefficient is 8. Now, if that was the exercise you were given, right there, then you'd be looking for two numbers whose product is 15 and whose sum is 26. That's what you'd want. But that's not what was given. You were given this. So what I'm suggesting is that the most notable thing about this exercise is that it's not monic, what was given to you. Which means that the technique on the previous page simply will not work. Won't work. So the previous page it looks like this. If you want to factor something that looks like this, so factor x squared plus bx plus c. So this is monic because it's 1x squared. Then you want to find two numbers. So find p and q such that the sum is what? B, right? The middle number. And the product is what? C, the last number, right? So that's the monic case. Now, in the non-monic case, the question is factor a multiplied by x squared plus bx plus c. The distinction being that now it's got a coefficient, leading coefficient of a. So we still want to find p and q that satisfy two conditions. And the first condition is the same. P plus q is b. So that's the same. And the second condition is that p multiplied by q is c. And if I stop there, then they'd be exactly the same. And so far they're no difference. The difference is right here that I'll write in red. C multiplied by a. That one little difference. So now over here, in this context, what is a? 1. So it was always there. Can you see it? All right. So the exact same thing that, making a table and finding two numbers and messing around and doing all that technique still works here. It's just now we're looking for a different product. Okay, so now we're going to make our search. So we want to find two numbers, p and q. And we want it to be the case that on this specific exercise that p plus q is what? Which one? The middle number. 26, right? And then p multiplied by q should be 15, the last number, multiplied by 8, the first number. which happens to be 120. Okay. But now this table, messing with this table is exactly the same as before. All right. So looking at this, I can see that, okay, I want the product to be 120, and in particular that's positive, which means that concerning the signs, what should be true about the signs of the numbers that I'm looking for? They're going to have to be both positive or both negative. Can't have 1 and 1. Similarly, because the sum is positive, that's telling us that in fact what?
They'll both be positive.
They're both positive. Because if they're both positive or both negative, and the sum is positive, then the only possibility is that they're both positive. So that's nice. The negative numbers are out. Okay. So how about, I don't know, 2 and 24. So that's a reasonable pair to inspect because, well, when you add them, you get 26. But, but what?
48.
Yeah, when you multiply them, you get 48. Okay. Fine. How about 3 and 40? I claim that's a reasonable pair to inspect. Why is that pair reasonable to inspect? Right, because the product is correct. But the sum isn't, right? So, you know, again, for the 10th or whatever time, you can see it's easy to get one of these and maybe not the other. And the real trick is finding two numbers that satisfy both conditions. Okay, so does anyone have a good suggestion? 20 and 6, okay. So that's a good suggestion because, well, when you add them, the sum is right, and when you multiply them, the product is right. Okay, so we found a pair of numbers that does what we wanted. Okay, now if we were in the monic case, then basically we'd be at the very end. The only thing remaining would be to write down the answer. So now I'm going to write something down, and it is going to be incorrect. So if you're going to write down what I'm about to write down, please carefully note that it is incorrect. So I have a question. So then, is it the case that this is equal to that the answer is w plus 6 multiplied by w plus 20? But besides my, you know, disclaimer saying that this is not going to be correct, besides that, why is this not correct? Okay, so I heard a lot of reasons. So, you know, what was given is not monic. Okay, in the first place. Now, any factorization can be quite readily checked. How do you check it?
Expand.
Yeah, by foiling it out, right? What do you get if you FOIL this out? Well, you get what? You get w squared plus 20w plus 6w plus 120. Is that going to work? That's not going to work for a variety of reasons, right? First reason is that this result is monic, but what was given is not monic. Another point of view could be to say that the constant term for what we were given is 15, but the constant term for what we're suggesting is 120, and those aren't the same. All right, so this just isn't going to work. Nevertheless, this right here is actually a pretty common answer to this mistaken answer to the question. Okay, rather, the way to proceed is that we have to do that same splitting thingy that we did on the previous page. So we're going to take that, (8w squared plus 26w plus 15. And we're going to use these two numbers that we found to split the middle term. We're going to say that this is 8w squared, like that. And then plus 6w plus 20w plus 15. And it will not matter what order you happen to put these in. So if you were working ahead and you wrote 20w plus 6w, it'd be just fine. Won't matter. So all that table work up there was just so we could make this split. Now that we have 4 terms, we can make 2 groups of size 2. And then in each group, we can factor out the GCF. So in the first group, what's the GCF? 2W. And in the second group, what's the GCF? 5. Is there any question about finding the GCF in each group? Okay, then for the first group, where we factored out 2w, what needs to go in there? (4w plus 3). Okay. And in the second group, where we factored out 5, what needs to go in there? Again? What? Yeah, again, right? So then, to be clear. So what if you're doing this and, you had a brain cramp or whatever, and you wrote 4w and then like plus 10. I don't know why. Maybe because instead of doing, 15 divided by 5, you did 15 minus 5. Somehow something didn't go right. Well, this should be a red flag for you. Because at this place in the exercise, it must be the case that these two are the same. If you get to this position and these two are not the same, you have made an error somewhere. Somewhere you made a mistake. So this method is kind of nice in the sense that it has this very loud, shiny signal that's telling you whether or not you did it right. Okay. So we have the same thing. And then, if I was covering up an A, if this was 2WA plus 5A, then A would be common and we could factor it out. Okay? So I'll factor out that common bit, 4W plus 3. And then what goes in here? 2W plus 5. And then, if you're not confident that this is the answer, how can you always check? Foil it back out, right? So do you see that at the top of the page, where I wrote the little hidden block, it says, that's the answer, that's the final line, right? The final response, and then this is what we found. So are those the same? Yeah, they're the same. The factors are in the opposite order, but it doesn't matter because multiplication commutes. And to be clear, what's being graded is this whole process. Okay, of carrying it all out and showing all your work and all this stuff. Any question about it? All right, let's do the next thing. So one item that's in the current written homeworks is, you know, last week or I don't know, maybe 2 weeks ago, I can't remember, we said this, that the binomials a plus b and a minus b are said to be conjugates, and when you multiply them together, all of the mixed terms cancel, and you end up with this: a squared minus b squared. And you know, this has a nice way to say it in English, that the product of conjugates is the difference of squares. All right. So this comes about in the following kind of way. So what we want to do is factor. So if I give you something that you can write like that, if you can ever get it to that place, then you can factor it like that. Okay. So if I write, if I say, let's consider this one, x squared minus 16. Okay. So now I'm going to ask a question that's a little bit slippery. Sort of, you know, word lawyering. I'll ask, okay, so what I've given you, is it expressed as the difference of squares? And the answer is no, it isn't. It's not. Because, you know, we want it to be one thing squared minus another thing squared. So it's not currently written as the difference of squares. Now, there's two terms, that term and that term. That term is a square because it's thing squared. That is not expressed as a square because it's just 16. It's not expressed as a square. Now, here's a different question. Is 16 expressible as a square? Yes. Yes. So what I'm saying is that you know, we'd like to be able to say that this is x squared minus thing squared. So can you tell me what goes in there? 4, right? Okay. So now this is the difference of squares, expressed as the difference of squares. Okay, so then you could say that therefore the answer is x plus 4 multiplied by x minus 4. Any question about that one? All right. Now you might reasonably say, well, okay, I guess the distinction is it currently expressed as the difference of squares, and can it be expressed as the difference of squares? That's a little bit subtle. But what if here's the reason for the distinction in the language, is that what if I say, instead of x squared minus 16, what if I say x squared minus 15? All right. So, is it expressed as the difference of squares? No. It is not. Is it expressible as the difference of squares?
Just not with integers.
But not with integers, right? So then the question is you know, if I write x squared minus blah, and I ask, what can I write in there to make this right? The square root of 15. That's what gets put in there. What's the name for the number that when you square it, you get 15? Square root of 15. What's the name of the number that when you square it, you get 16? Square root of 16. 4 is another name for that number. What's the, you know, that number just happens to have two names, right? What's the name of the number that when you square it, you get 10? Square root of 10, right? Now, so that number is 15. Is it expressed as a square? No. Here's how you can express 15 as a square. Now, that's a curious way to write 15, but that's 15. Any question about that? All right, so now let's do another one that hopefully will elucidate this a little bit for you. So how about x squared minus 36? So now, on the one hand, comparing this to just x squared minus 16, I suspect you could probably just tell me the answer right now. But I'm going to write something that might be just a little bit disturbing to you. I'm going to say that this is equal to x squared minus the square root of 36 squared. And so this is equal to x plus the square root of 36 multiplied by x minus the square root of 36. And there's nothing wrong with that. Now you might say, okay, well when you wrote that, I kind of thought that it would be x plus 6 multiplied by x minus 6. And I can just say, well, it is that. It is that because it just so happens that, you know, numbers have more than one name. You know, there's the number that's 6, and another name for 6 is the square root of 36. It's just another name for it. So what I want to be clear about is that, you know, when I ask this question as the opener, and I ask something like, is there, you know, what number can I square to get 16? Most folks can say 4, basically without any hesitation. But then I say, okay, how about 15? Can 15 be represented as a square? And at that point, there's usually a pretty big pause. And there's usually at least a handful of people who will say, no, you can't do it. But as somebody said, here's what I'm asking. Is there a number that squares to become 15? Some folks said no. The answer is yes. What number squares to become 15? Square root of 15. Now if you say no, then here's what I suspect, is that when I say what number squares to 15, that's what I'm saying. And I mean, what real number can I square so that I get 15? And what you're probably hearing is what integer squares to 15. And I agree entirely that there isn't one. There isn't an integer that squares to 15. But there is a number that squares to 15. All right. So to that end, how about something like 9x squared, and then subtract, you know, I don't know, 10. So we want to factor this. All right. So what we'd like is to express it as the difference of squares. Well, okay. So, you know, we want it to look like, I'll do it one at a time, and I'll say, okay, I'll deal with the first thing and leave the second term alone for a moment, just so we're doing one thing at a time. And I'll ask, okay, what can I write in those parentheses? 3x. Right? So that 10 is still that 10, so we didn't mess with it, so it's fine. And then, yeah, 3x all squared is in fact 9x squared. So this first term is a square now. All right. So now I'll just copy that one. And then write this here and then ask, okay, what do I need to write in those parentheses? Square root of 10. So can you see now it's the difference of squares? Now that we've arrived at that position, you know, you just, blah, that's the answer. So the answer is 3x plus the square root of 10 multiplied by 3x, 3x. Minus the square root of 10. Any question about that? All right. Good. Next thing. So one thing that we talked about, you know, back when we were first talking about FOIL, is that we have this nice formula. A plus b squared is a squared plus twice ab plus b squared. So that's just an immediate consequence of FOIL. Now, what if I say, okay, that's fine, but what about this one? So if I say that this is one thing there, and then the second thing is a plus b, and now instead of squared, how about cubed? We want to answer that. Okay. So I'm going to leave us a box here to write the answer in. Now, how can we get the answer? How do we get it? Well, here I think is probably the best way that we have currently available to us. I could say that, well, remember that that thing cubed means make 3 copies of that and multiply them all together. Also, because of the rules of exponents, we can say that, well, it means a plus b squared multiplied by 1 more a plus b, right? That's what it means. But, you know, conveniently, for a plus b squared, we've got a rule for that. So I can just replace that with that. Now what? Yeah, now we have to distribute, right? There's no better thing. So I'll distribute like this. You know, so it would look like a squared plus twice ab plus b squared multiplied by a plus a squared plus twice ab plus b squared multiplied by b, and then, you know, just distribute this into there and this into there. Okay, so then doing that, a cubed plus 2 a squared b plus a b squared plus a squared b plus 2 a b squared plus b cubed. All right. So now we'd like to collect things that are the same. So there's currently 6 terms, right? 1, 2, 3, 4, 5, 6. 6 terms. And, you know, for each one, we want to figure out, you know, what other terms are like it. So in this case, to say that 2 terms are alike is to say that concerning the 2 letters, the 2 symbols, A and B, you have to have the same quantity of those. So have a look at this term. That's AAA. Right? Because remember, A cubed is AAA. How many other terms have AAA? None, right? So this one's all by its lonesome there. Okay, so A cubed. Now, that one has a coefficient, and that's nice, but the only thing that matters is the letters, in a sense. So this is AAB. Are there any other terms that have AAB? Yeah, that one right there, right? So this is 2 AAB, and this is 1 more. So how many of them altogether? 3, right? So this would be plus 3 a squared b. Okay, similar story for this one. This is a b squared. So so do you see that there's two more of them right there? So this would be 3ab squared. Okay, and then what's left? The b cubed. So, you know, what I'm saying is that here's a nice formula. A cubed plus 3a squared b plus 3ab squared plus b cubed. All right. So then next, I could say, what about a plus b to exponent 4? What could we do?
Take our answer there and just subtract another AB or A plus B.
Right. So do you see that we could say, well, this should be a plus b cubed, and then one more a plus b. And then you could do a little bit more algebra circus, and come to the answer. Right? And then suppose that I said, well, the one I'm actually interested in is a plus b to exponent 9. Then you can imagine how much, you know, how many pages we'd fill to get to that place. Okay, so there's actually a better way. There's a better way to go about this. So here, I'd like for you to observe the following pattern. So for this one, a plus b squared. Now I'm going to write out its formula in a way that you wouldn't normally write it. So instead of writing a squared, I'm going to write AA. I'm going to write AA, and then plus 2AB, and then plus BB. And then normally, when there's just one of them, you know, a squared, you don't write the coefficient 1. But I'm going to go ahead and write it. I'm going to write one of those and one of those. So one of those, two of those, one of those. Similarly, for a plus b cubed, writing the formula out in that same kind of way, we'd have AAA plus 3 AAB plus 3 ABB plus BBB. And again, you would normally write a coefficient of 1, but I'm going to do it. And here's what I'd like for you to observe. That when the exponent is 2, how many terms do we have in the formula? 3 terms. When the exponent is 3, how many terms? 4. Do you have a suspicion? When the exponent is 9, how many terms will there be? There'll be 10. There'll be 10 terms. Similarly, when the exponent is 2, notice that every term has how many letters in it? 2, right? AA, AB, BB. And when the exponent is 3, every term has 3 letters in it. AAA, AAB, etc. So if I was interested in a plus b to exponent 9, there'd be 10 terms, and every one of them would have 9 letters in it. There'd be one of them that had 4 A's and 5 B's. And the question is that, well, what would be the coefficient? What would be the number in front? Right, so here what I'm saying is that we've got 1, 2, 1. Here this is 1, 3, 3, 1. How many is there going to be for each of the further we go down the line? So we're not going to be able to say it today, but that's going to be the first thing that we cover next time. Does anyone know the name of how to get those numbers? Yeah, it looks like that. It's shaped like a triangle. It's called Pascal's triangle. Okay.
Pascal.
Yeah, so we'll use that next time to figure out those coefficients. So please turn in the this one on the way out.
Of this one.